Hello, everyone, and welcome to Metcalf Institute's webinar series as part of our Climate Change and the News Initiative. This is a program that we started in 2013 to help journalists cover climate change by introducing them to researchers who are doing climate change science all over the country, looking at a lot of different aspects of climate change impacts, as well as climate change adaptation and climate change mitigation. Today, we're really pleased to welcome Dr. Erika Lentz, who is a research geologist at the U.S. Geological Survey's Woods Hole Coastal and Marine Science Center in Woods Hole, Massachusetts. Dr. Lentz is actually a graduate of our institution, the University of Rhode Island, which is where Metcalf Institute is based, where she received her PhD in geosciences. And prior to her position at the USGS in Woods Hole, she actually had a Mendenhall Research Fellowship, also with the USGS in Woods Hole, and a postdoctoral research fellowship in the same place. Prior to that, she worked with the National Park Service and had a number of other training programs as a doctoral student that really prepared her to talk about climate change impacts in a variety of ways, but especially focusing on coastal ecosystems and how sea level rise is affecting those coastal systems. So I'm really pleased to turn the mic over to Dr. Erika Lentz. Erika, I think that you're on mute.
There we go.
All right, that sounds great.
Now everybody's caught up. Hi, thank you to you, Sunshine, and to the Metcalf Institute generally for inviting me to speak today. And I eagerly have welcomed this opportunity because we have been looking at this problem for a long time with a really fabulous group, and it's something that I very much want journalists to have access to and understand. So with that said, I will share my screen. And let's make sure this is working. All right, are you able to see my screen, Sunshine?
Yes, yes, I see.
Okay, all right. So as I mentioned, this was a fabulous group that I was able to work with, really tackling this problem, which was looking at a more comprehensive representation of the coastal response to sea level rise. This is work that was published in a Nature Climate Change article in March, and is where there's lots more information available to the general public through a project page that I will be showing you later in the presentation. So an important point that I want to make at the outset is that drowning is really not the only scenario for sea level rise impacts across coastal landscapes, simply because they vary considerably. We've got a lot of ecosystems and people living in close proximity to one another, as the slide shows. And can you verify that you can see my pointer, Sunshine?
I can't. Oh, yes, I can see it. It's small.
Okay. All right. All right. So I'm gesturing with my pointer to the upper left-hand side of this forested area. We also have marshes. We have barrier beach systems, mainland beach systems, coastal bluffs, engineered structures, riprap, groins, jetties, and of course people, all sharing space And we know these different environment types are all going to respond differently to the sea level rise impacts problem. For example, marshes might be able to vertically accrete and adapt to sea level rise impacts if their overall health is good from the outset. People are certainly going to start to alter their systems as well as some of these impacts become more prominently felt. Bulldozers on the beach is a great example, and replenishment. So we know there's both a dynamic response element, and then there are more the flooding and erosion risks associated with sea level rise. So because determining the response can be so difficult, typically the way sea level rise, at least broad scale predictions of sea level rise have been presented to date, are through these inundation models, or what are commonly referred to as bathtub models. So here in the slide, you can see in the upper left-hand corner, we've got the NOAA sea level rise viewer, and in the upper right, we have the Climate Central's Surging Seas viewer. And what these models assume at the outset is that the landscape response will be the same everywhere, which is simply a drowning response. So if you picture a bathtub and picture the land as represented by the walls of the bathtub, and simply add water to this bathtub, this is very much the visualization that these sorts of models are giving you. So typically they share a few things in common. They have have a really nice slider bar where you can simply raise the water level to whatever you might deem appropriate as a decision maker. They integrate high resolution elevation data. So a lot of data from LiDAR, for those of you that are familiar, that are tidally adjusted. And they do provide broad regional coverage at very high resolutions. Their limitations are that they typically do not associate a time frame with a flooding increment. So if you are a decision maker and you're looking for a realistic sea level scenario for, say, the 2030s or the 2050s, because that's the planning horizon you're working under, it can be a bit confusing to figure out what's a realistic scenario if you don't have that information already ingested and available to you. And they may or may not include an uncertainty as an estimate associated with them. And even if they do, it's not necessarily straightforward in terms of how to integrate that information with the depictions that you're seeing. And furthermore, as I was just showing in the previous slide, we know that this problem is more complex than simply drowning. There's a variation in response across the landscape. A really unique aspect of this problem for me was that I got to work with resource managers from across the coastal Northeast at the outset of this project before any of the research had begun. This was through a structured decision-making workshop hosted by the Fish and Wildlife Service. Specifically, this was a group organized by the North Atlantic Landscape Conservation Cooperative, which is an extension of the Fish and Wildlife Service. And what we were really discussing during this week was what the sea level rise information was that these decision makers and managers needed in terms of their day-to-day. What were they looking to preserve and protect, and how was this information going to support those needs? So what is structured decision making? It's a formalized decision-making process wherein you think through every step of the problem to be solved at the outset. And this requires you to often go through multiple iterations of the problem. So we first defined a decision problem, which is shown in the purple box at the top. Objectives shown in the blue circles that, if met, will mean that the problem is being adequately addressed. And alternatives on the bottom shown in green, or management actions. These are adaptive management strategies that will be taken in order to ensure the objectives are achieved. There are more steps to the process, but this is as far as we made it during that week. And this was a considerable effort just to get the people in the room to agree to these. What you'll see the things I want you to take away from this slide is that you'll see that the sea level rise impacts piece of this was really viewed as central, which is shown in the purple diamond, central to this problem. First and foremost, the managers recognized that they needed to know whether or not land was going to be there at a first cut, so that they could be developing informed adaptive management strategies and identifying areas that might serve as good buffers, mitigators, or offer some trade-offs moving forward. So for example, if you're looking at a beach that's rapidly eroding, you might want to find whether alternatives are available before you're building a new pavilion in a particularly vulnerable area. So these were the sorts of questions that they were wrestling with. And I came away knowing that the problem really had to be addressed at both a broad scale and fairly high resolution, so that this information could support some parallel habitat modeling that was ongoing, and so that from a bird's eye view, managers could really start to identify areas that were vulnerable and areas that might serve as some potential alternatives or offer some trade-offs for areas that we were standing to lose. So we really broke the problem down into two outcomes. The first is inundation, which we recognized is a perfectly appropriate response at some places, such as hard shorelines, rocky shorelines, heavily engineered or developed shorelines. These are places where a straightforward inundation model is perfectly well applied, but that this just is not an accurate way of depicting the sea level rise impacts everywhere. And here is where we also evaluated the potential for dynamic response. And here we've defined it as the ability of an area to either maintain its initial land class state, so a beach stays a beach, or transition to another non-submerged state, such as a forest transitioning to a marsh. So these included all the areas that we anticipated would had some natural response or potential for adaptation moving forward. Beaches, unconsolidated cliffs or bluffs, barrier islands, marshes, uplands, etc., as well as a human response component too, because certainly we know humans are going to start to alter these systems moving forward, and that is an additional dynamic component to factor in. What we did, we produced results for from Maine to Virginia at fairly high resolution, so that this could work with the habitat models that were in development. We built on an existing inundation model structure, because these inundation models did include broadly the resolution and the coverage that we were looking for. But we incorporated vertical land movement. So this is the moving up or down of the Earth's surface in response to glacial isostatic adjustment, groundwater withdrawals, sediment compaction, etc. We included a pretty robust workup of uncertainty, both in the data and our process understanding. And we also associated a time horizon with those sea level rise projections. So you could say, in 2050, what is the most likely sea level rise scenario for my area? And then we added dynamic response information, and this was really largely tied to land cover. And what we know about the different response rates of beaches versus marshes, et cetera. And we also wanted to make it possible to update the model by adding new and better data, as well as information as they become available. So we used a really flexible approach in doing this, and that's what I want to spend a little bit of time on in the next slide. So here, we used a Bayesian network, which is a probabilistic modeling approach or framework. And I wanted to provide you with a relatable example at the outset, because I think this really helps you to wrap your head around what they're doing. So very simply, they're a way of considering or taking into account things that you know well about your system. coupling those with things that you know less well, but you know are certainly factors in affecting a given outcome. And what these provide you with is the probability that you will observe a certain kind of outcome. So something that's near and dear to my family's heart is my husband's commuting time to Boston. We hope it's going to take him an hour most of the time. Often it takes him longer. So what are some of the things that he knows before he leaves the house that affect his commuting time? Certainly the weather, whether it's snowing or sunny outside, the day of the week. Mondays tend to be the worst. The time of year, is it school vacation week? These are all direct factors that he can account for early on. But there are also things he knows less about, but that certainly also affect his commute. Accidents, construction delays. We know these are largely tied to some of the knowns that we outlined just a moment ago. So for example, you're more likely to get an accident when the roads are really treacherous, but less likely to observe construction during those times. And certainly volume on the roads, as well as the time of year affecting those volumes comes into play. So what we can do is start to learn more in this approach about the relationships between these things that we know well and things that we know less well, because they all, of course, contribute to his commuting time to Boston. The really great part about this approach is that every time he makes a trip into Boston, he is collecting data, and we are learning more about the relationships among these parameters and these variables in the model. So every time he takes a trip is an opportunity for him to update these factors a little bit more, refine his probabilities, and become more confident in how long it's going to take him to get there. Let's look at what our model shows. So things that we knew pretty well and things that we knew less well are taken into account. Sea level rise projections, these are based on IPCC's RCPs 4.5 and 8.5, the vertical land movement piece that I mentioned earlier. This makes our sea level projections relative to a certain area, as well as elevation. These are all combined to give us what we're calling an adjusted land elevation or inundation level at the outset. So this is what's relatable to those inundation or bathtub models that I was explaining earlier. We then couple this inundation level information though with land cover information. And this is where we provide a prediction of the likely coastal response type, whether it's going to be a dynamic response, so it's going to stay above the water level, or whether it is going to become inundated. This is what some of our outcomes look like. So this is directly from the paper. You can see we have 4 panels. The 2 at the top show the 2020s predictions for the adjusted elevation range. So again, this is relatable to an inundation level or inundation model. And those from our coastal response type predictions. So for the same area, which is Prime Hook National Wildlife Refuge, you can see that in the 2020s, we're predicting 70% of this area is going to become submerged through an inundation approach. So everywhere you see blue are areas that we are predicting to be under sea level, under that sea level scenario. Compare that to the coastal response type predictions, where the red indicates greater likelihood of dynamic response. Beige indicates that we're nearly totally uncertain about what the response is going to be, and blue indicates greater likelihood of inundation. So in our coastal response type predictions, we're seeing that 2% of this area is likely to have a coastal response falling below 50%, meaning that for 2% of this area, inundation is more likely than a dynamic response. So that's a fairly big difference. It's definitely starting to capture some of the variability and the complexity that we know to be inherent in looking at the landscape response to sea level rise impacts. By the 2080s, a lot more of this area is submerged, shown in the lower left panel. We're looking at a greater likelihood of more area inundating by the 2080s in our response predictions. So now we're seeing a lot of that beige turn to blue moving forward, but it's still not nearly the level of inundation or submergence that is represented by the inundation approach. So to take a few steps back, again, why this matters. So to date, this is channeling back to the inundation model again. If we picture, instead of a bathtub, we have a bucket, and in that bucket we have rocks that represent the land. What we're adding to the story with this coastal response information are two more buckets, one filled with sand and one filled with sponges. So as we add water to the rocks, the response is again fairly straightforward. As we add water to the sand, we're going to see that sand start to move around and shift. As we add water to a sponge, we're going to see it absorb some water. We're going to see it expand to a certain degree. What we found in our paper, though, is that 70% of the Northeast landscape is likely to respond like the latter two buckets. So this is an incredibly important response component that previously hadn't been well represented by these broad scale sea level rise inundation models. And I mentioned this is a probabilistic approach again. So if we were to put on a parachute and drop down to one particular point represented by the black arrow in the map, one particular point in the marsh on this landscape, we can see that we have shifting probabilities through time. In the 2020s, we're fairly confident. So the probability is on the y-axis and the decade is on the x-axis. We're fairly confident that we're going to have a fairly low projected sea level range. But we're seeing as we move through time that distribution is widening. We're less confident, but that our projections are actually higher. If we look at our coastal response likelihood down below, where orange represents dynamic response and blue indicates probability of inundation, we're seeing initially that marsh has a greater likelihood of dynamically responding, but that through time, by the 2080s, we're less certain about what that response outcome is likely to be. We're less certain that marsh is likely to keep pace with sea level rise by this point. Largely because the sea level projections are higher, but also because we're factoring in other uncertainties. The thing that I'd like you to come away from this, or something I also want to remind you of, and part of the impetus for doing this is that decisions really are being made both now in both the short and long term with information that didn't adequately capture or depict the sea level rise response to date. And so what we were really trying to do and have done in this approach is figure out a way of taking into account all the uncertainty that we know exists, putting it together in a way that I think is still fairly intuitive and digestible from a decision-making standpoint in terms of casting things in the form of probabilities or odds, and telling you more about the complexity of these systems. I mentioned that more information is available on our project website. The URL is shown here. You can find more information about our structured decision-making process. You can download the data, and we are developing some decision support tools, but those are still in the works. So again, the things that I hope you're coming away from this presentation knowing. First is that a large portion of the landscape really wants to change in response to sea level rise. And what our approach is showing is when and where this is more likely to happen, and also where we're more uncertain and where we need more information moving forward. However, just because you're really uncertain about a certain area doesn't mean you can't act. If you know there's a 50% probability that an area might inundate moving forward and you're looking to invest millions of dollars in an infrastructure project, this can actually tell you a great deal. And finally, that the coastal response to sea level rise will require some difficult choices. A lot of folks have asked us, well, is dynamic adaptation then a good thing? Is this a more positive outcome for the landscape moving forward. And I guess I would say it depends on the decision that you're trying to make. If you're a homeowner and you're living on a barrier island where stuff is supposed to move, where sand is supposed to be moving around, inlets are forming, things are overwashing, those natural processes are occurring, and there's a high dynamic response likelihood, this may or may not be a favorable outcome from the perspective of home ownership. Another great example is areas where farmland is transitioning to marsh. From a habitat creation perspective, this could be a really great thing. But if you're the farmer that's standing to lose a lot of land due to marsh conversion, this can certainly be a challenge. So with all of that, I'd like to acknowledge the following people, and I'll take any questions that you might have.
Wonderful. Thanks so much, Erika. That was great. And I realize I have my camera on now. Okay. That was fantastic. I really appreciate it. So I have a couple questions for you. The first one is about the sea level projections that you used for this. Mm-hmm. So I think that if I understood correctly, you were saying you used the most recent IPCC projections. Is that correct?
Yeah, we used scenarios 4.5 and 8.5 for those of you that are in the guts of this and curious. But these were based on 24 global climate model projections. And the thing that I'd like folks to know at home is that, am I?
There you are.
Okay. Now. Is that these projections were actually provided to us probabilistically. So Radley Horton at Columbia University provided these in percentile ranges. So those probability ranges that I was showing earlier, we already had what was the most likely scenario for a given time step when we were integrating this information. So that was incredibly helpful. We have a wide range of potential. We had a broad range of potential ranges, but what was the most likely out of the gates, and we could use that to inform how we proceeded.
So I was asking that because there has been a lot in the news lately about different scales of sea level rise projections, and so I'm wondering how and whether that was captured in your study?
Well, what's interesting is the last range, the 0.75 to 2 meter range, is the most likely range that we're using for the 2080s predictions. What will be interesting is, in light of some of the more recent information on the increasing rate due to Antarctic ice sheet collapse, whether those probabilities our confidence levels are going to become more likely. So we might weight those outcomes potentially more heavily. But again, given the flexibility of this approach, we can easily do that. So that's a really cool piece of this.
Great. And so because you talked about uncertainty so much in this presentation, for good reason, are the biggest uncertainties in your model with regard to the sea level rise projections or in other places?
Yep. Sea level rise is a huge uncertainty component in our model. But another area where we have a great deal of uncertainty is in some of this process response to sea level increases. So for example, we're still trying to figure out how rapidly marshes may or may not be able to keep pace with sea level rise moving forward. And so marshes are fairly uncertain in our model at low levels, but as we learn more about marsh adaptability moving forward, again, we can update that uncertainty and that process-based understanding moving forward.
Gotcha. What about human response uncertainty?
Yeah, that's a huge area of uncertainty for us, and that will be a very interesting piece to watch play out, I think, moving forward. It's definitely going to be a socioeconomic problem, and it will be very location specific. So I think people are really the wild card in our model, and we're still really waiting to see, as these impacts become more broadly felt, how people are either collectively going to be responding, and how that might be generalizable at the scales that we're looking at, or how variable that response is in and of itself. So,
great.
Yeah.
And another question was about the decision support tools that you said you're working on. Can you tell us more about that?
Sure. So we're looking at breaking our predictions down by land cover type, and looking at how different land cover types are responding through time. And so we're trying to make some interactive web tools where you can go to a certain location and look at the various time steps and how that uncertainty element plays out in the marsh predictions moving forward, for example. Mm-hmm. And we're re-engaging with the decision makers in refining and developing these, which has been really a fun outcome of the structured decision-making process as a whole, as we have now this network that we can tap back into and use for feedback and to make sure that this is immediately useful to the intended users. So. And are we back?
Are we back? Can you hear me?
I think so, yeah.
Okay. I just asked, are you planning to do this in other parts of the country?
I think that is the next step that we've identified. Yeah, this has been very well received. And so I think the interest is definitely in expanding this. And I also have interest in drilling down and looking at some areas where we have more locally specific information. So there are some marshes that have been really well studied, for example. So looking more at where we have more specific information and how that updates our probabilities and our understanding is also something that we plan to do.
Great. Is there any last thing that you would like to add? We've come to the end of our half hour here, but I'll give you the last word if you'd like it.
I guess I would say that I think this is looking at local impacts, because I know a lot of folks will want to relate this back to their specific areas, that these problems are not unique. And what we've produced is a broad approach that can be scaled down to understanding generally what you might use and how you might move forward in terms of decision making. So,
great. Wonderful. Well, thank you very much, Erika. That was fantastic, and we're glad to have featured you as one of our webinar speakers. And so, if we will be posting archiving this webinar on Metcalf Institute's YouTube channel. It should be live later this afternoon. So if you're viewing it live or going to the archive, be sure to look through the remainder of our many, many videos on the YouTube channel. There's a lot of resources there featuring scientists from all over the country talking about a lot of different aspects of environmental science and environmental issues. Also, I'd like to note that our next webinar will be not next week, 2 weeks from today, May 17th at 1 p.m., featuring Dr. Catherine Hayhoe from Texas Tech University, who will be talking about some of the actions necessary for us to actually achieve the goal of capping overall temperature increases on the globe to 1.5 degrees Celsius. So we look forward to joining you then. Thanks again, Erika.
Thank you.
All right, take care.
Okay.